Take 3. It's a recording thing. I usually record second period, but my little adapter is I'm making changes. So.
I don't trust
I like how you say that, but like the majority of the time we see you just recording us.
Yeah, I usually record second period. So, but yeah, it's so that way if you like get hung up on the acid basic, you can always go back to Google Classroom and then download the thing on YouTube and watch it. It's super cool. If you have your litmus paper test lab, put that in the box and then take out paper for notes. We're talking about the pH. So on Friday, you watched some videos about the pH scale and what pH represents. So we're going to talk about that today, and then we're going to do some calculations. The P part of pH, no one really knows why it's P, but it is. The P of the pH stands for negative logarithm. So you should have encountered logarithm over the last, maybe this year, maybe last year, in your math classes, and we're going to review what logarithm represents. Logarithm are base 10 exponents. The H in the hydronium, the H in the pH is hydronium ion concentration. And once again, hydronium is the H3O+. So when you put P and H together, you get the negative logarithm of the hydronium ion concentration. P, negative logarithm, H, hydronium ion concentration, the negative logarithm of the hydronium ion concentration. Now, I didn't make the rules, don't be mad at me, but for some reason the P is negative logarithm, so high hydronium concentration means low pH. High hydronium, low pH. So higher pHs are usually from 0 to, or sorry, higher pHs are basic, high acidity is from 0 to 7. So when a solution has a pH of 4, it's an acid, and 10, it's a base. I didn't make the rules, that's just the way it is. So scribble what you want to scribble, and I have a table over there we're going to create, and we're going to talk about what the actual pH represents in terms of concentrations. So I have a table up here, molarity, 10 to the negative x, logarithm of P. If I had a solution that had a concentration of 0.1, 0.1 is equivalent to 10 to the what power? Okay, so good. I'm glad we're reviewing logarithms. 0.1 is 10 to the what power? 10 to the negative 1 power. Okay, 0.1 is 10 to the negative 1. Like 10 is 10 to the first power, 100 is 10 to the second power, 0.1 is 10 to the first power. Does anyone know what 10 to the 0 power is? 1. 10 anything raised to a 0 power is 1. Yeah, you can ask your math teacher about why that is, and maybe he or she will explain it to you, depending on what kind of mood they're in. But so 0.1 molar, if you have a 0.1 molar solution, that has a 10x of 10 to the negative 1. The logarithm is the base 10 exponent. So the logarithm of 10 to the negative 1 would be just negative 1. And P is the negative logarithm. So if the logarithm is negative 1, the P would just be 1. Continue our pattern. If you had a solution that had a concentration of 0.001 molar, that would be equivalent to 10 to the what power? Negative 3. 1, 2, 3. 10 to the negative 3 power, which means it would have a logarithm of what? Negative 3, and a P of what? 3. Exactly. So you're seeing the pattern. There's a pattern developing here. And if you had a concentration of 0.00001 molar, this would be equivalent to 10 to the what power? Negative 5. Pretend it's a 5. 10 to the negative 5. So the logarithm would be negative 5, and the P would be 5. Lastly, one where the concentration is 0.000001 molar. This would be 10 to the negative 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 10 to the negative 7. The logarithm would be negative 7, and the p would be 7. 7. It's okay. I do the same thing. See the board, you can go right through it. So 7. Okay. So the logarithm is the base 10 exponent. The p is the negative logarithm. So the first thing we do when we take our concentrations is we convert them to powers of 10. Now, here's the good news. In this class, everything is going to be a power of 10. It'll be 1 times 10 to the negative 3. 2, 1 times 10 to the negative 2. 3, 1 times 10 to the negative 3. Okay? So 4 will be 1 times 10 to the negative 4. Nothing, we won't do like 2.8 times 10 to the negative 3.2. We're not going to do that. Everything's going to be whole numbers. Powers of 10 with whole numbers. So, for the most part, you won't even need your calculator most of the time. Okay. Give me a thumbs up if this logarithm thing makes sense to you. Okay, so hopefully this is a review. If it's not, well, welcome to logarithms. Next, what does this mean? Well, if instead of these being just solutions of concentrations, if instead they're solutions of acids, then the P becomes a pH. Which means if you have a solution of an acid that's 0.01 molar, this is 10 to the negative 2, the pH would be 2. So if the H3O concentration is 10 to the negative 2, the pH would be 2. If you had an H3O concentration that was 10 to the negative 4, then the pH would just be 4, which by the way is 0.0001 molar. So that's what pH means. It means the negative logarithm of the hydronium ion concentration. Now, there are two really cool relationships that allow us to do really easy math in pH. And this is what they are. There's this number called the ionization of water, and it's 10 to the negative 14. Okay, pretend it's a negative 14. So 10 to the negative 14. And it's equal like any other equilibrium expression as the cation times the anion. So 10, slow down, fires. 10 to the negative 14 is equal to the hydronium ion concentration times the hydroxide ion concentration. The hydronium ion concentration times the hydroxide concentration will always be 10 to the negative 14. It's really neat. So if your hydronium ion concentration is 10 to the negative 2, then your hydroxide concentration has to be 10 to the negative what? 12. Yeah. For those who remember their logarithms, when you multiply numbers with exponents, it's like adding the exponents. So this has to be 10 to the negative 14, which is 10 to the negative 12 times 10 to the negative 2. If you had a hydroxide concentration that was 10 to the negative 3, and again, it's less equal 10 to the negative 14, then the acid has to be 10 to the negative what? 10 to the negative 11. Okay? It's a really nifty relationship, and there are no exceptions. Okay? So it's hydronium times hydroxide equals 10 to the negative 14. Cool? Okay. Now there's one more really nifty relationship, and I don't know what law it is. There's some mathematical law that says when you take the logarithm of a product of exponents, it's actually the sum of their exponents. In other words, if you take the P of the H3O concentration, you get pH. If you take the P of the OH concentration, you get POH. And if you take the P of 10 to the negative 14, you get 14. So you have two really handy relationships. This one and this one. The hydronium ion concentration multiplied by the hydroxide ion concentration will always be 10 to the negative 14. And the pH plus the POH will always be 14. It's really neat. So if you have a solution that has a pH of 6, the pOH has to be 8. Exactly. If you have a solution with a pH of 2, the pOH has to be 12. If you have a solution with a pOH 8, then the pH has to be 6. There are 4 values: the hydronium, the hydroxide, the pH, and the pOH. If you know one, you know all 4. There's 4 values you need to calculate, but if you know one of them, then you know all 4 of them. Because if you know the pH, you just subtract it from 14, and you have the pOH. If you know the pOH, subtract that from 14, and you have the pH. If you have the hydroxide concentration, divide it by 10 to the negative 14, you have the hydronium concentration. If you have the hydronium concentration, divide that by 10 to the negative 14, and you have the hydroxide concentration. And if you have the pOH, take that, 10 to the negative that, becomes the OH concentration. If you have the pH, 10 to the negative that, becomes the hydronium concentration. So if you have a solution that has a pH of 6, then you know the hydronium concentration is 10 to the negative. If the pH is 6, the hydronium is 10 to the negative 6. Good. And if that is the case, then you know pOH has to be what? 14 minus 6 is 8. And that means the OH concentration has to be 10 to the negative 8. We'll be practicing this quite a bit. Okay. That's the really beautiful relationship with pH. If you know the pH, you automatically know the pOH. If you know the hydronium concentration, you automatically know the hydroxide concentration. If you know any one of those 4, then you know all of them with these basic relationships. Okay. Questions? Okay. It might seem like a lot, but I guarantee you it is not. It's actually really, really easy. When you actually do some practice, you're going to get in the groove and you're just going to fly right through it.
Do the test now.
Okay, test ready? Okay, here comes the test. So, little question, something to talk about with your neighbor, just so you understand the pH scale in general. If a solution increases in pH, does it become more acidic or does it become more basic? So, take 5 seconds, chat with your neighbor, and the little red hand is on the 8, then we'll talk about it. Okay, so if you think that when a solution becomes higher pH, you become more acidic, raise your hand. Nobody. If you believe a solution becoming higher pH becomes more basic, raise your hand. Good, because high pH means basic, low pH means acidic. I didn't come up with that, that's just the way it is. No questions? Then off we go. Okay, so here's a fun little diagram. It's right out of a textbook somewhere. I pulled it off the internet, I think. But it's out of a textbook. So if you're sitting up front, you have a fun little pH cheat sheet right up here. Yeah, sitting up front, you can see it. Here you go. Take your head, sunglasses, take your binoculars, look up there. There it is. Sorry, it's so small. But again, so we have pH 0 to 14. 0, we have battery acid, stomach acid. 14, we have lye, household ammonia. Now, I will tell you, in this class, there are no exceptions. In reality, if you go on and take more advanced chemistry classes, you'll learn that the pH scale can go negative and can go over 14. But not here. Okay, we're just going to... Yeah.
You scared me for a second, so there's no exceptions. Like when you a test, you get one question wrong, it's all wrong.
Yeah. Yes, that's exactly it. Welcome to 1984.
What's lye?
Lye is rat poison and drain cleaner. Lye is just a fancy name for concentrated sodium hydroxide. Remember when we did the gold penny lab, those little tablets? That's lye. Yeah. Yeah. So it's good for killing things.
Wait.
Yeah.
What's a little packets that you put in your food that says do not eat with it?
Silicates. There's a couple different ways, depending on what they want to do. It's usually a compound to absorb moisture. So that way they put it in the material, that way the things don't rust between here and China. Yeah. It's usually something that absorbs moisture.
Jerky.
And jerky, yeah. You don't want your jerky to get all moldy, so you take the moisture out. Good question. Okay, so if you understand, here's a summary. In pure water, there's a perfect balance of hydronium and hydroxide. It's just really neat. So if you see a concentration of hydronium that's 10 to the negative 7, your hydroxide also has to be 10 to the negative 7. If you have a pH of 7, that means you also have to have a pOH of 7. There will always be a perfect balance of hydronium and hydroxide. If you have a pH of 6, that means your hydronium concentration is 10 to the negative 6, and your hydroxide is 10 to the negative 8. If your pH is 4, that means your hydronium is 10 to the negative 4, and your hydroxide 10 to the negative 10. Okay? It's always a really beautiful balance. 4, 10, 10 to the negative 4, 10 to the negative 10. 7, 7. 8, 6. 9, 5. It's a perfect balance. Always. Because that's why water is so cool. Okay. So again, acids shift things towards hydronium, bases towards hydroxide. There's your auto-ionization. This is the two relationships I wrote up there. So this is just a summary page. Next, I want to do some sample exercises on actually calculating pH and pOH in our heads.
Okay.
Any questions before we do those sample exercises?
No, thank you.
Amphoteric? If you want, yeah. We actually talked about what amphoterism is. Amphoteric means a substance that can act as an acid or a base. If you want to neutralize a bunch of acid, you can use water, and the water will act like a base. If you want to neutralize a bunch of base, you can use water, and the water will act like an acid. It's called amphoterism. Yeah. So if you got too much acid in your tummy, you can eat some base. If there's too much base all over the place, you can add some acid. So, which is why you're afraid when you're doing too much acid, you need to drop the base.
What?
Yeah, Nicole's a little.
I got it.
Gabe wasn't paying attention. It was totally intended for others of you. But anyway, moving on.
Oh no, I heard it.
Okay,
What
good.
did I miss?
No.
When you take too much acid, you gotta drop the base. Like pH.
Melt your face.
Melt your face. Okay. So now we're going to look at the hydronium and hydroxide concentrations. There are two big pitfalls here. The biggest pitfall is just not reading the exercise. So read the exercise before you answer. The other pitfall is remembering this. If it's asking for a P something, it's going to be a whole number between 0 and 14. Okay? pH is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? If it's asking for a P, it's going to be 0 and 14. If it's asking for a concentration, then it's going to be 10 to the negative something.
Wait, hold on one second.
Okay. P will be a whole number. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. If it's asking for a concentration, then it's going to be 10 to the negative something. So don't get those two mixed up. That's pretty much the only place people go sideways.
It was from 0 to 14,
Yes.
and the other one was...
The concentration is going to be a power of 10. It will always be a power of 10. Concentration will be 10 to the negative 2, 10 to the negative 3, 10 to the negative 14, or some decimal, 0.001, 0.00001, or so on. So, you got to make sure you're reading the exercise and answering the question it's asking. So it says, what is the pH, whole number? What is the concentration, 10 to the negative something, or a decimal? So here we go. If you had a solution that was 1 times 10 to the negative 4 HCl, first thing you need to ask yourself, is this an acid or a base? When we look at the molecule, it's 1 times 10 to the negative 4 molar HCl. We've used HCl. HCl is a what? Hydrochloric acid. Good. So again, I'm not going to be tricky. There's not going to be, all the acids will have an H in the front, all the bases will have an OH in the back.
Okay.
H in the front, acid. OH in the back, base. Yeah.
I have a question. It's
Sure.
kind of, it has to do with HCl. So, like for creatine, there's creatine monohydrate,
Mhm.
and then there's creatine hydrochloride. So, like, I don't get, is it just different? I know what it does because HCl doesn't retain water, but why?
it's exactly like you said. It's to cause it to dissolve. They take molecules that will not normally dissolve, and they make it a hydrochlorate, so it will dissolve. It's just they take the molecule. Your body wants the molecule, but it can't dissolve in water, so it makes it very, very difficult to digest. So they add a hydrochloride to it to make it be able to dissolve and digest. So a lot of your drugs that you take will be a hydrochloride, because that's just the simplest way to make something dissolve in your body. Otherwise, it goes right through you, and you'll get any benefit. Okay, so 10 to the negative 4, that means this is our acid, so our hydronium is going to be 1 times 10 to the negative 4. Make sense? What's going to be our hydroxide? 10 to the negative 10. So if our hydronium is 10 to the negative 4, our hydroxide is going to be 10 to the negative 10.
So always that has to go negative 14.
Yep. Concentrations always have to be 10 to the negative 14. And that means our pH is going to be what? 4. And our pOH is going to be 10. 10. See how that works? That's the pattern. It never breaks the pattern. It just follows the pattern over and over again. So now we have nitric acid. You can see the acid in front. 10 to the negative 3 nitric acid. What's going to be the hydronium concentration? The hydronium. 10 to the negative 3. This is an acid. So our hydronium is 10 to the negative 3. That makes our hydroxide 10 to the negative 11. And now that we have hydronium and hydroxide, we can identify the pH here as 3 and the pOH as 11. Questions so far? You feeling good about this? Yeah. This is something you can do? Okay. Now this one's a base. This is sodium hydroxide. This is the base we've been using in class. And the concentration of the base is 10 to the negative 1. So does this give you hydronium or hydroxide? It gives you hydroxide. So the hydroxide concentration is going to be, the hydroxide is going to be negative 1. That makes the hydronium negative 13.
Wait, how do you know if it's like, oh, this is a base?
Base.
Oh, so every
Acid.
base is like
Acid.
H3O.
Yep. So there's not going to be any crazy exceptions. All of our strong bases are going to have an OH at one end. All of our strong acids are going to have an H at one end.
This is backwards, so then like the pH for that would be 13, and the pH would be...
Right.
Yep. So the pH is going to be 13, the pOH is going to be 1. Question?
When you're putting like these problems into an example,
Mhm.
you don't use like the
Decimal?
no, what it's giving you like sodium hydroxide. You would put like Na when where H3O is.
Nope. We just care about the OH and the H. So we only care about the H for the acid and the OH for the base.
Oh, so it's gonna give you one or the other. every
Yep.
time.
It's going to give you one or the other. And then you will use what you know here to solve the other 3.
Okay.
Yeah.
I like writing down the whole hydronium hydroxide, we just put like 10 to the negative 13.
You need to say what it is. Yeah, so you do need to write the hydronium is 10 to the negative 3. The hydroxide is 10 to the negative 1. And again, in this class, everything's going to be 10 to the negative 1. So you can just say 10 to the negative 13, 10 to the negative 1. Don't have to worry about the 1.0 times thing, because again, when you take more advanced chemistry, you will have to see 3.2 times 10 to the negative 4.8. 1.9 times 10 to the 2.3. Anyway, not this class. Yeah.
So if we're like giving, this is like the first one, like 1 times 10 to negative 4, and then we see that that is like a base. No, or is it acid?
It's acid.
It's an acid, yeah. So that means like the acid will be like 4.
Yes.
Like the H and the base will be.
Yep. And again, good question up there. If you have a 10 to the negative 7, that means the other one's also going to be 10 to the negative 7. That's neutral. Otherwise, whichever one is bigger tells you which is the acid or base. This one, hydronium's bigger, acid. This one, hydronium's bigger, acid. This one, hydroxide's bigger, base. Okay?
Whoa.
Okay.
How is hydronium bigger on the second example?
Because 10 to the negative 3 is bigger than 10 to the negative 11.
Oh, okay.
Then negative 3 is 0.001, then negative 11 is 0.000000001.
Got
Shall we move on?
Yes.
Moving on. More practice. Okay. So I'm going to have rapid fire. This is the lightning round. Here we go.
11.
I have a worksheet for you so you can do practice on paper. If a solution with a pH of 3 has a pOH of 11. A solution with a pOH of 10 has a pH of 4. Good. A solution with a pH of 4 has an H3O of 10 to the negative 4. Okay? So if a solution has a pH of 4, the H3O is 10 to the negative 4. Concentrations are always going to be 10 to the negative something.
Wait,
Uh-huh.
wouldn't it be 10 to the negative 10 if it's...
No, because this is the pH and this is the H.
Oh, okay.
So you can basically think of the H3O concentration like this. H3O concentration is 10 to the negative pH, if you want to think of it that way. Next, be careful with this one. A solution of pH 8 has a hydroxide concentration of what? 10 to the negative 6. Well done, yeah. Exactly. So if you took the 2 steps, you got it exactly right. If you said, well, my pH is 8, that means my pOH is 6, so that means my OH has to be 10 to the negative 6. I'll say that again for people who just are tuning in right now. If you got the pH 8, that means the pOH has to be 6 because of this relationship. And if the pOH is 6, the hydroxide concentration is 10 to the negative 6. Okay. Give me a thumbs up if you got that. All right, cool. Bright bunch. Moving on. 10 H3O concentration to the negative 4. What's the pH? 4. H3O concentration 10 to the negative 10. What is the pOH? 4 again. Good. So the pH had to be, and the pOH had to be, okay, so you do 2 steps. H3O makes a pH of 10, means the pOH is 4. OH is 10 to the negative 6, what's the pOH? 6. OH is 10 to the negative 1, what's the pH? 13. Good. So you realize the pOH was 1, that made the pH 13. Awesome. Banging right along. If the OH is in negative 12, what's the H3O? 10 to the negative 2. Good. So if the OH is 10 to the negative 12, the hydronium is 10 to the negative 2. And the last one, if the H3O is 10 to the negative 4, what's the OH? 10 to the negative 10. 10 to the negative 10. Okay. So that's all the practice we're going to do together. I'll give you a worksheet in just a little bit. There's 2 things I want to talk about. Questions?
Slow down.
Okay. So let you exhale as I pass out a little acid-based handout. This is not the worksheet. This is just a fun little worksheet. This is a fun little handout I came across.
This is a fun little worksheet.
It's not a worksheet. It's just a fun handout that I came across, and I'm like, oh, that's kind of cool. It lists a whole bunch of common acids and bases. So this is something you can take with you when you go to your chemical engineering course in college.
Oh yeah. So I'm definitely have this stuff.
No, they're going to be memorize these. Ugh. I don't remember having to memorize any of this stuff. It's just one of those things you memorize on accident. You just use them enough that you just kind of remember what they are.
Yep.
Like I remember oxygen.
Yeah, exactly. Okay. Are we ready to move on to new concepts before we get the really easy concepts?
Yes.
Okay. So neutralization. Neutralization is a special kind of chemical reaction where an acid and a base come together to make water. It looks like this. So our acid is nitric acid, our base is sodium hydroxide. They break into their ions, and those ions come together and form water molecules and a salt. A salt is anything that's just a cation and an anion.
What's a good way to write that down?
You could just do that becomes this if you want. If you don't write the ions, that's fine. So this is a special kind of reaction that you learned about, has a name. You learned about it in December and January, and the initials are DR. Does anyone remember what kind of reaction this is called? Because there's 3 multiple choice questions on your semester exam about the reaction types. I'll give you a hint.
It's a reaction.
No. But remember there was synthesis, combustion, decomposition, and then the replacements, single and double replacements. So this is a double replacement
I like that.
because they switch places. The H finds the OH, and the Na finds the NO3. So remember, there will be exercises there will be multiple choice questions on your semester exam about the 5 reaction types: synthesis, decomposition, combustion, single replace, and double replace. So those are going to be on there. So that's neutralization. So you take a strong acid, add a strong base, you get water and a salt. In fact, I don't do it in this class. It used to be done, and then people thought, it's probably not a good idea to drink things in class. But there used to be the science teacher would be like, look at this strong acid. You pour it over some medical, like, look at this strong base. You pour it over something, and they're like, that's nasty. Like, look what I can do. And they pour them together and they drink it. Yeah, because you could, technically. If you had a strong acid and a strong base, and they were of the same concentration, you could pour them together, and what you get is salt water. That's it. Totally, you could just drink, swim around in it, like in the ocean. But generally, we don't do that anymore because that's probably a bad idea. We don't want to tell kids to drink things in class.
Why not? Just salt water.
Yeah, but it's just that's a bad example. But in this case, you could do it because they neutralize each other. Okay, the last thing I want to talk about is something that came up a couple times in the video on Friday, and that is indicators. Indicators are really neat. Indicators are chemicals that are one thing in an acid and something else entirely in a base. They actually change. And because they change, sometimes they become different colors. The transition interval is the range at which they change. And there's 2 really valuable pH indicators. If we had more time and we were doing titrations, we would use phenolphthalein. Yeah, you can't read that very well. It's phenolphthalein.
Just outline
Phenolphthalein.
it. Blue on red on blue. That's the way to do it.
Anyway, phenolphthalein. You can look it up. The one we're using tomorrow in lab, we have a really fun lab dealing with the pH thing. We're going to make a rainbow of colors. And the one we're doing tomorrow in lab is called universal indicator. Universal indicator is nifty because it has 6 or 7 transition intervals, so it can be multiple colors, giving us a whole range of pHs. Take that. Sugary kernels. Okay, so that's all I have for today. The remainder of time, work on your pH practice exercise.